cloud.
Okay, sorry for the delay. I went to spare engine and walking up the hill took a while. Okay. If you don't know me, I'm a faculty here. I've been here since 2002. And actually, I finished my bachelor's in 1989, and my bachelor's thesis was on AI, okay, in 1989. Okay, so that's why they call it AI winter. It didn't. It was a different kind of AI. Okay, more like rules based. Okay, and so I thought. I also thought I thought about LLMs and AI, but I've seen many other talks, so I thought I'll do something different. I'll talk about a classical research topic. So my general area of research is in networking and sensing. Okay, and this work is on networking and wired networking. How do you make internet more robust? Okay, resilient to failures. So this is how we do traditional link state routing. Okay, so imagine you can think of, we are talking about what happens in backbone networks like Verizon, AT&T, right? In their networks, imagine they use something called link state routing, and that's called open shortest path first, like OSPF. The core idea is something like this. Imagine I'm the router. I have some links. Okay, I form a what is called LSA, link state advertisement, that says I'm the router. I have these 3 links, and this is the cost of each link from me to my neighbor. And I form a link state advertisement. I send it to my neighbors. My neighbors send it as is to their neighbors, and so on. So everybody in the network, within that domain, they get my link state advertisement, and like that they get it from different routers. Then they form a complete topology. Okay, on that topology, each router independently computes its own shortest path. Okay, and then it computes what is called a forwarding table, also called FIB, forwarding information base. That means if that is a destination, this is my next stop. If that is a destination, this is my next stop, and so on. So that is the forwarding table. And now once the forwarding table is computed, now that is in hardware, and the packets come, look up and send. And that has to be real fast. We're talking about millions and billions of packets per second. Okay. But what we are talking about is happens in what is called a control plane, where one router talks to other routers to gather the topology and run algorithm like Dijkstra's to compute the forwarding table. And that is the traditional routing. So now imagine I compute my forwarding tables and everything is going great, and suddenly there's some change, like a link got cut. Okay, right? Interface failed, things like that. Okay, so that's a link state change. When that change happens, I tell my neighbors, okay, like the nodes adjacent to the failure, notice that first, and then they form a new LSA, and they send it to their neighbors, and neighbors send it to their neighbors, and so on. Everybody in the network recompute their forwarding tables. Okay, right? So once they recompute, and then once they cut, everybody has a new information, everything will be consistent and everything will be fine. But during the time, from the point of failure till the time where every router in the network has recomputed their new forwarding tables, there is a discrepancy. It's possible that I'm aware of the failure, but he is not. Okay, so it's possible that when I send a packet through him, and because there's a new path goes through him, but he thinks based on the old information, the path goes through me, then you can have routing loops. Okay, and the time between the time of failure and when everybody converges, that is called a convergence delay. Okay, and during the convergence delay, we can have this kind of routing loops and packet drops. Okay, right? So the question is how to make sure the goal is it should be disruption free. That means we should be able to forward continuously regardless of the failures. Failures are kind of natural, they happen. Even if failures happen, we want to reroute, and we want to reroute within, they have a time like 50 milliseconds. And if everything happens, as long as you don't have a disruption, not more than 50 milliseconds, you can also have IP, what should I say, phone calls or voice over IP kind of service you can provide. Okay, right? So now how do you ensure this kind of continuous forwarding? That's one goal. Another is you want to route towards optimal paths, shortest path routing. You don't want to have long detours. Okay, so these are the 2 key goals: continuous forwarding and so shortest path forwarding. Okay, right? So now, so this is how traditional things happen. Okay. Now, these are the possible things can happen when it's a link down. Why would the link go down? One could happen that is called what is called planned link shutdown. So for maintenance, they bring a link down, okay, intentional. Or you can have unplanned failure where something happens. These things happen. There's a study on how often these failures happen. They happen fairly frequently. Now let's look at the planned failure scenario. Okay, so yeah, we are bringing down for routine maintenance. Okay, and but even then, forwarding is possible. Okay, forwarding loops are possible during convergence. So this is the simple topology I use for illustration. Okay, so here these are all whatever I'm showing these letters. They're all routers. Okay, real routers. Okay, but we show them as nodes in a graph. Okay, and A to B is a real link, but we show that using edge. Okay, and the weight 6 is somehow conveys how good is that link. Lower the weight is better it is. In practice, they make that link weights inversely proportional to the bandwidth. Okay, wider bandwidth, lower weight. Okay, and this is also one knob they have for network administrators. They change these link weights to control how traffic flows in the network. Okay, traffic engineering, they gather this kind of traffic matrix through ingress and egress. I have a network. My traffic enters this network through these ingresses, and traffic exits through these egresses. And now I have a traffic matrix. And how do I balance that traffic through my network? So that's called traffic engineering. They don't do this dynamically, like every per packet or things like that. They do once a month or things of that nature. And they may plan for Thanksgiving or things of that nature. Right? And just that is called traffic engineering. And the control, the knob they have is adjusting these weights. You change these weights, you adjust how the traffic flows. So now we have these routers, then you have these links and edges. Okay, and given this, now we want to compute a shortest path. Let's say, suppose you take something like destination F. Okay, right? So let's say just for this scenario, let's assume that the destination is F. Okay. Now instead of showing all the entries, I'm just showing what will be the forwarding entry only for the destination F. Okay, imagine that I want to send a packet from A to F. For A, the next hop along the shortest path is X. Okay. For X, the shortest path along the shortest path is B. For B, it's E and F. Right? You can see why, because the shortest path, you can see the path length. Okay, 1 plus 1 is 2, 2 plus 2 is 4, plus 2 is 6. So the shortest path from A to F is AX, B, E, F. Okay, right? Compared to any other path. Okay, so this is what typically happens. Right? So now everybody converged, everybody has a correct routing, forwarding the entries, and everything is going good, right? Now imagine what happens. We want to bring this link down. Okay, right? So B to E, we want to bring it down intentionally. Okay, but we can still route around it. It didn't fail. Okay, so I can use it. I keep it on till everybody has new tables. Then I can remove that link. Okay, so that is the idea of planned shutdown. We'll talk about unplanned later. Okay, now in this case, now imagine, like let's say bringing that down is like changing the cost from whatever value to infinity. That means there's no link. Okay, let me get a clicker. Oh, it's working. I didn't notice. Mm-hmm. Okay, right. Okay, so now we want to tell everybody that the cost went up from 2 to infinity, right? We informed everybody. Now everybody is recomputing, but every time everybody takes different amount of time to recompute and update them. Each one is doing independently. Right? So imagine that X is sending a packet, right? X has the before it computed, this is the old path. It has to go from B to E, right? And sorry, X to B, and then over B to E, the link is still on. Okay, it's not brought down yet. Okay, and then packet goes to F. Everything is fine. Okay, nobody has new tables. Everybody has old entries. Okay, now imagine X recomputes. Okay, right. So X has a new entry. X has accounted for the failure. Okay, So now the new next hop from X to F is A, because B is down, right? The packet has to go that way, right? Okay. So now only X has computed, right? So now we say that X is in what is called AC era. Okay. Everyone else is in BC era. Okay. That means BC is for before convergence, AC for after convergence. Okay. Right. Somehow only X has recomputed, has new tables. Everyone else has old tables. Okay. So now when X sends a packet to X sends a packet to F, it sends to A. Right. A still has old entry. It will send to X. Okay. Right? And that will loop. Okay, so this is an example of a loop that can happen during convergence because of the discrepancy between my view and your view. You have an old entry, I have a new entry, and so the way the link state routing works, only everybody has consistent view. Now this is the problem, right? So what is the fix? Okay, so there are many fixes for this. One of them is what is called loop freak. This is for graceful one called ordered fib updates. Okay, somehow you want to make sure you update this guy first, then this guy in particular order. Okay, here is an example of that, right? So imagine in this scenario, right? Suppose you update A first. Okay, right? So A has a new entry without BE. Okay, so A to F, the new next hop is C. Okay, so now then you update X. Okay, right? In that order. Okay, so when you do like that, if the packet goes like this, okay, right, everything will be fine. Okay, right? So the ordered updates are done such a way. If you use old paths, everything is fine. If you use new paths, everything is fine, right? It's never a loop. Okay. So, for example, we think we didn't show the scenario of this. Let's go back to the scenario. Okay. All right. Only A is updated. Let's say. Okay. If the packet has to go from A to F, it will go ACEF. Okay. If the packet has to go from X to F, it will go XBEF. Okay. Right. No loops from anybody. Okay. Right? So there is a specific order. This first, then this, no loops, and continuous forward. No problem at all. Okay. But this is only for planned shutdown. Okay. Right? So now that is so you can come up with an order. It's possible to, given a topology, it should be in this order. Okay. So what is the downside of this? Now, because of this, when you have this kind of order, that means you need some kind of signaling between routers. Let's say I want to update my fib. Okay, I have to wait for someone else to say, oh, I have to compute. Who should I wait on? Okay. Oh, he has to update first, only me. Then I have to wait for him to tell he's done updating. Then I update. Okay, right? There has to be some kind of signaling protocol. That means your routing protocol is changing. You have a typical routing protocol. Just implement this, you have new kind of packets, some control information. Right? So now, then there is another proposal. Oh, let's not change the protocol. Is there a way to do this without changing any routing protocol? Okay. Right? This is what is called progressive link increments. Okay. So no change to the routing protocol. How does this work? Okay. Very interesting protocol. Okay. So in this, let's say I want to go, that link is going from 2 to infinity. I don't go from 2 to infinity. Okay. I go from, in this example, I go to 2 to 7. We'll see how we come up with 7. Let's not worry about it. Let's say we tell everybody the cost of this length went from 2 to 7. Okay. So then we see that doesn't matter. Let's say this guy X computes it. Okay. So in the case of X, after, even if it becomes 7, 2 to 7, the shortest path from X to F will be 1 plus 7, 8 plus 2, 10. Okay. Compared to any other path, it will be 11 otherwise. You see that? Okay. So even after the cost change goes from 2 to 7, the shortest path from X to F is still XBEF. Okay. Is that clear? Right. Now everybody updates with 7, and we can guarantee that no loops. Yeah.
I'm an ILAC engineer by trade, and what we did to get around this is we moved to head-in switching versus tail-in switching. So node B can actually reroute its own traffic if you use head-in switch traffic engineer tunnels rather than tail-in switch.
Yeah. So another thing we don't use any.
Goes the egress interface. The ingress interface controls the reroute.
I see. Right. So the way we do is no tunneling. Okay. But you don't need to set up any protection in tunneling. I'll show some examples of what is other approaches. Okay. But anyway, so again, I'm talking about this as an academician, okay, from academia. I don't have any industrial experience. Okay, I'm treating it as a graph algorithm and things like that. Yeah. Okay. It's good. We can once I finish all the ideas, you can see where we stand.
And if B2E is a transatlantic link or a transoceanic link, it's even more important.
Right.
Because of the latency.
Right. Yeah. Okay. So when you go from 2 to 7, okay, everybody has new information. Goes from 2 to 7. We can guarantee there is no loop. Doesn't matter who updates when. Okay. And then with that, let's say packet goes that way, no problem. Okay. And then you go from, then this guy updates, let's say, it'll be with this, it'll go this way, right? When that is 7, shortest path from A to F will be ACEF. Okay, you see that? So doesn't matter who updates when, everything works correctly. Okay. Now you go from everybody observes this new state. It's not 2 anymore. Everybody knows it's 7. Okay. Now you go from 7 to infinity, then no problem. Okay, right? Because A is already goes through the different one. Okay. So this is the idea of, instead of going from 2 to infinity in one step, we are going in this kind of what is called progressive increments. Okay. 2 to 7, 7 to infinity. 2 steps. And at no stage, no loops, no drops. Okay. And no coordination between any routers. Each one is doing independently. Okay. So this idea got best paper award at a conference called IEEE Infocom. That's like a main conference in networking. Okay. Not our idea. Okay. This is not my idea. Okay. So now these are the 2 general ideas to deal with. How do we do convergence without loops and things like that? Okay. But the problem with both of them, they elongate the convergence process. Okay. Now, what is the problem with, let's say, link failed and everybody converts? The delay is convergence delay. If you elongate it, if another failure happens within that time, you are not ready to handle it. Okay. So it's good if the convergence delay is short for 2 reasons. One, you have a optimality of routing. You're always using the shortest path. Another one is that you're reducing the chance of another failure happening within the convergence. So now that is all planned shutdown. Okay. Now we can have unplanned failures. Okay. You can have fault interfaces, router crashes, things of that nature. Okay. Right. Now, so failures happen. On the other hand, you have this expectation of this called 5 nines availability. 99.999% of the time you want the network to be available. Imagine you just sometimes let's say recently our spectrum, the internet is down in our house for like 1 hour or something. Everybody didn't know what to do, right? So imagine how, and also in the working day, right? So things like that, you, regardless of the failures, you want to be robust, resilient. Okay. So now that's where was called IP fast reroute. Okay. So you don't tell anybody that the link is down, but you want to reroute. Okay. That is the idea of fast reroute. Okay. Without any convergence. My link is down. I don't tell anybody the link is down. I do something such that packets come to the point of failure, they get rerouted to the destination. Okay. Now there are some of these are the fast reroute approaches. One is called loop-free alternates. It's possible that I have one best next hop, but instead of that, I can use some other next hop. Okay. So it's not there's only one way. There are many ways, many paths. Right. So the find a next hop which doesn't cause loops. Okay. It's called loop-free alternate. Okay. So there are many alternates exist, but only thing is you can't guarantee 100% coverage. What it means is I can't use this method and guarantee for any failure I'll find a path. Okay. That's the limitation. Very simple scheme. Okay. Then another is called multiple routing configurations. For the same topology, I have many routing configurations. In one routing configuration, some links exist. In another routing configuration, some other links exist. Okay. So anytime I want to forward, I say, oh, this packet is being forwarded using routing configuration 1. This packet is being forwarded using routing configuration 2, like that. Okay. So in that case, but you need to carry anytime you can come up with this kind of lot of backup configurations, but packet has to carry this configuration information so that when the router gets a packet, it knows which configuration it should use to route it. Okay. So, but now we are changing the packet. You're putting some information, additional information in the packet. Changing the IP header is not easy. There are a lot of it's pretty, it's not easy to upgrade everywhere to account for that to handle new information. Another approach is called not via addressing. This is a very interesting idea. Okay, this came from Cisco. Okay, so the idea is that imagine the packet has to go from me to him, right? So then when packet reaches the point of failure, I take the packet, I put in another packet, okay, encapsulate it, okay. So, and the outside packet, I give the address of the next guy, and what is a special address called not via address, okay. So now everybody knows when they route that address, they shouldn't include this link, okay, in the computer forwarding entry for that address, okay. Special addresses, okay. So, but it requires this kind of encapsulation. At the point of failure, I take the packet, put in another packet, and route around the failure. It reaches that point on the other end of the link, and that they decapsulate and regular forwarding afterwards. Okay. So encapsulation, decapsulation, some overhead. Okay. So now this is our idea. It's called failure inference based fast reroute. No changes to the packet. Okay. No modification to the packet. No encapsulation. No tunneling. None of it. Okay. All using regular packet headers. Okay. So this is our idea. Okay. Called failure inference based fast reroute. Okay. This is how it works. Okay. Imagine this one is like this is how it was. Right. So our idea is that apart from this, right, these are called next hops. Okay. Right. Whatever we have are called next hops. So we find that imagine take A. Right. A has 3 interfaces. Okay. 3 line cards. Okay. Right. So typically the router architecture is that we normally think of it as a one forwarding table at A. Okay. But that's not what happens. A has 3 copies of the same forwarding table. Okay. So that because imagine A to X link is 10 gigabit per second link. Packets are coming. I want to look up at the line card speed. So they put the copy of the forwarding table in the card so that you can do the forwarding table lookup and forwarding at that line card speed. So effectively, you have 3 copies of the forwarding table. Okay. So it'll say X, on X to A, it'll say X, C to A, it'll say X, D to A, it'll say X. 3 interfaces, same information. Okay, saying that the next hop to go to F is X. Okay, follow? Identical copies, 3 copies. Okay. That's what happens in the regular routers. Now, our idea is let's do something different. Okay. So you have, remember that I'm saying there are 3 copies of the forwarding entry, but in one copy from X to A, I say it's D. Okay. What is called back hop. Okay. In case packet reaches packet reaches A from X, the next hop is D. But it reaches me from anyone else, my next hop is X. Okay. All this with respect to destination F. Okay. Remember that all this is in the context of F. Every destination, this is different. Okay. You follow? So for destination F, I have 2 kinds of entries. One is called a back hop. In case packet comes back from my usual next hop, okay, that is what I call back hop. My back hop is D. Okay. My usual next hop is X, like before. Let's not worry about how I got D. Let's say somehow we got that. Let's say we install those entries. Now let's see what happens. So imagine the link failed, B and E failed. Okay, right. Now B recomputes. Okay, now packet has to go from X to B, right? So X doesn't know about, remember that link failed, nobody knows about the failure except B and E. Okay. Only the nodes adjacent to the failure are initiate rerouting. No one else knows about it. Okay. No new computation. Okay. Now packet has to go from X to F. It'll go from X to B like usual. And B knows B is down because it's adjacent to me. Okay. According to B, the next hop is X. Okay. Right. That X. Right. So now when packet reaches X, it is coming through that back hop. The next hop is A. Okay. You follow? And now when it reaches A, the next hop is D. Okay. Okay. So this is how the idea works. It's all pre-computed. Okay. Right. So a link failed. We didn't tell anybody. We didn't initiate any convergence. We just initiated a reroute. And everybody, all that they are doing is they are just doing the usual lookup and send, lookup and send. Only difference was previously we had 3 copies of the same entry. Now we have 1 copy different from the other 2 copies. Is that clear? So that is the idea. So from a packet from C to A, next hop will be X. Packet from D to A, next hop is X. But packet from X to A, next hop is D. Only one entry will be different. Okay. It doesn't matter how many links I have. Okay. Yeah.
Why can't this go from A to C, E, and F? Oh,
Yeah. Right. That's a good point. Okay. That's a beautiful point. So how come A to F, the next hop is back hop is D? Why is it not C? Okay. Right. We'll come to it. So this is, suppose, imagine somehow we computed. Now you can see how it works. Okay. No, you don't tell anybody, and we have this continuous forwarding. Okay. No loops. Now, how do we compute those? Okay, this is the idea. So it's a fast reroute without we didn't set up any tunnels or anything like that. No encapsulation, decapsulation. Okay. But what is different is that we normally use, if you're given a destination, who is my next hop? That's a normal question in forwarding. Now we are asking, given the previous hop, okay, my incoming interface, given the incoming interface and destination, I choose the next hop. Okay. So that's what I call interface specific forwarding. Okay. That is the change. But this change doesn't cause any change in the forwarding plane, because we are doing interface specific forwarding anyway. It's just that all those copies are identical before. Now I'm making one copy different from the rest. Okay. Now the question is, how do I know which one failed? What should be my alternate route? I got a packet from this way. I have no idea what failed because nobody told me. Okay. Right? So how do I know what packet failed? What should be my next hop? Okay. Right? So that's what I use, what is called a key link. If when the packet came through X to A, right? X is my next hop. He should be sending the packet to me. If he's sending packet to me, that means there's something unusual happened. Okay. What failure could cause the packet to come back from my usual next hop in the reverse shortest path towards me? Okay. Right? I try to infer that failure. But this is not on the fly. We do it in advance, compute the entries and keep it. Okay. Right? It's not per packet on the fly computation. It's all pre-computation. So we do that key link computation. And then once you do that, I can eliminate the key link and compute the backup. So this is all not done on per packet, we do in advance. Okay. Here is an illustration of how we do it. Okay. So we'll show only what happens on X to A. Okay. Think of X to A. Okay. If packet has to coming from, if the destination is B. Okay. So that means B is the destination and this is the incoming interface. Okay. And key is the key link. Okay. So we are asking, what are the key links corresponding to the interface X to A with respect to destination B? Okay. Right? So X to B, right, should not send the packet to A normally. Okay. Right? On the other hand, if XB fails, X to B link fails, then X would send it to A. You follow? Right? So that is XB. Okay. We are saying that if the link XB fails, X would send the packet to A when the destination is B. Okay. So that is the key link. Now, on the other hand, if it is when X sends to if the X sends to C, it is usual. Nothing new to fail, right? X to C is 5. Any other way is longer. Usual. Nothing unusual. So no failure would cause that. Okay. Right. Similarly, for D, you don't need a failure for that to happen. Now for E, right? Why would X send the packet to A? Okay. If XB fails, B would send. Okay. XA would send. If BA fails, BE fails, then also do it. Do you follow? So if this fails, X would send to A when the destination is E. Okay. And if this fails, even then it would send it. Okay. So there's a possibility of two failures. Failure of XB or failure of BE would cause the packet from X to E to come through A. Follow? We don't know which one failed. Nobody told us. Okay. But we have a proof that instead of, we can remove all the links that might have caused the packet to come, or remove one link called a key link, you have the same effect. Okay. So effectively we call the key link as the farthest one. Okay. This could have failed, and let's say the key link is BE. Okay. We remove this when we compute the path to E. Okay. So now comes the similar, now we are asking why is D? Okay. So imagine what happens when XB fails, X to F would come to, if XB fails, X to F would come to A, through A. Is that clear? Okay. Similarly, if BE fails, B to F would come through A. Okay, you follow? Similarly, if EF fails, it will also come this way, because this guy is computing the shortest path from U to F without the failure. The shortest path is this. Okay, you follow? So if this fails, or this fails, or this fails, any of those three failures would cause the packet to come to A from X. Okay. So now the key link here is EF. Remember that of all the links, we pick the farthest one and we bring it down. Okay. That's what we call a key link. Okay. Now we can remove those key links and compute. Okay. It would look like this. Okay. That is what I'm calling backup forwarding table. Okay. This is used only when the packets come from X to A. Okay. Similarly, I'll compute one for C to A, D to A. I'm not showing them. Okay. Right. You follow? In the one forwarding table, we have three forwarding tables. Okay. But previously also we had three, but they are identical copies. Now they're slightly different. Okay. Follow? Yeah.
So are you proposing to extend OSPF?
No.
Protocol?
No change to OSPF. Because through OSPF, I get the topology. Okay. What I'm changing? Yeah. Okay. What I'm changing is the computation that happens. Okay. Messages are not changing. You're right. Okay. Yeah.
Extension.
Yeah. Exactly. Yeah, but no change to the messages. Changes to the way the forwarding tables are computed at one router. Yeah. I'm changing Dijkstra's algorithm, which is what is typically used, with my own. It's like a version of Dijkstra's algorithm.
But to do that, you have to compile your own version of Dijkstra.
Right. Exactly. Right. Yeah.
And then how do you relate what you're proposing versus MPLS has a backup path?
Right. So now, yeah, very good point. Okay. With the MPLS, you have to set up the label switched path. Right. Okay. You have to do label stacking. Right. Now I have to do all those label. What if this fails? One label switched path. Something else fails, a label switched path. So you'll find that you'll have n square kind of problem. Okay. You need to pre-configure many label switched paths.
Okay. But Juniper routers do that dynamically. So
maybe. But all I'm saying is that if they know this, they can implement this even more efficiently than how they would do. Okay, just that we are not there. If I'm in Juniper, I would say this. I can convince them this is better than whatever they are doing. Okay. But I'm just saying. But the thing with the MPLS is here we're only focusing on continuity, only delivering. No service level guarantees, nothing about congestion, none of that. Right. On the other hand, when they do it in the industry, they focus on many other aspects than just forwarding continuity. Yeah. So this doesn't deliver all those things.
Yeah, what we're doing, I used to work for CenturyLink and then Verizon.
Oh, right.
I'm a core engineer
by
trade. So what we were doing is we had an MPLS core, and then we were using QoS to map into the MPLS traffic classes. So we're doing it on the edge. Back end. No. But the pre-computed backup paths are very helpful when you have multiple links across the pond.
Right.
Yeah. So that's what we were doing. Like B2E, if that was London to New York, we would have multiple paths.
Right.
So it's still a problem, but when we moved to head-in switching and pre-computed backup paths, it was like near 100% effective. So where we would need this is like in the enterprise. Like on the edge.
Right. So is the idea clear? Okay. So this idea of key links, okay. I don't know which one failed. I'm guessing what would have failed. And among those failures, I pick the farthest one and I compute the alternate route. Okay. So now the beauty is that we can guarantee, even though this we don't know whether XB failed or BE failed or EF failed, I'm assuming EF failed and I say the next hop is D. Right? But we have a proof that even though give me any topology, okay, and as long as the destination is reachable, we'll find a path, loop-free alternate path. Okay, we have in the paper we prove it. Okay. So that is the idea. This is summary. No change to IP datagrams, no changes to forwarding plane. Okay. So even though I'm saying we need to, if I have, let's say my router has 10 links, then it has 10 forwarding tables. Okay, right? So, but it so happens that only one copy will be different, all other 9 will be same for that destination. Okay. So, effectively, what we have is 2 entries for destination: one usual next hop, one back hop. Okay. And then remember, he was talking about how long it takes to compute this kind of stuff, right? Sorry. Right. So this is the, normally it's E log V, okay, is the computation, right, for Dijkstra's algorithm. But for this, it's E log square V, okay, because we need to compute this back hops. Okay. And we guarantee that any router, any topology, we can deal with one single link or router failure. Okay.
Have you all tried to like integrate with like Zebra, like?
Yeah, but long, so that's because it's open source router code. There is an attempt, but we did say we generally, once we get idea and it's good, we lose interest. Now we want another idea kind of. So we, what should I say? Commercialization or public good is not as much as we hope that someone else takes and picks it up and runs with it. Okay. Now you're asking what makes me happy. Okay, right? So look at this. Okay, this made me very happy. Okay. This guy, you can go and look up this guy. He's a very good researcher from Sweden. Okay. Right? And he wrote a survey of these things. Okay. And in that survey, this is what he said. Okay. I don't know this guy at all. Okay. I happened to read this paper. It made me feel so good. Okay. So this, whatever I'm saying, FIR is FIFR are same. Okay. And this is what he said: gain significant risk following in the research community. Okay. And another thing that I like most is this elegant. Okay. We care about elegance. No other paper I've written got this kind of what's it, a survey saying something positive like this. Okay. Any questions so far? No. Now, so far, I only talked about rerouting. Link is down. Okay. How do we reroute? Okay. Right. So we are making sure there's a forwarding community, that we are continuously, destination is always reachable. Okay. But the problem is the path I take. The packets always go to the point of failure and then get rerouted. Okay. Right. The detour can be considered too long. Right? And also there's one issue. Another is that if another failure happens, we can only handle one. If another failure happens, we can't handle. Right? So now, so how do we do this convergence also? Okay. So we want to have continuous loop free forwarding. We want to do convergence, but we don't want to elongate the convergence. Okay. And we don't want to change anything. No forwarding protocol, forwarding plane changes, or no change to the routing protocol messages. So this is our idea called FIFR++. We'll see how it is done, called deferred backups and progressive increments. Okay. So now imagine that you do convergence with FIFR. Okay. When the link is down, right? So doesn't matter which, let's say it goes from 2 to infinity. Link is down. This is unplanned. Okay. Link is down. You tell everybody the link is down, and let's say X updates it. Okay. X says X is in AC state, and A is still in BC state. Okay. Right. Only X updated. A did not update. Remember that this caused a loop last time. Okay. But now no loop. Okay. Because when it sends this, okay, this guy will forward it to D, right? And packet reaches F. Okay. Right. You follow? Right. Whatever caused a loop in the past, because of FIFR, with convergence also, no loops. Okay. Now, on the other hand, when this is updated, packet will go from this way. Okay. Right. So when A is not updated, it reaches the destination through suboptimal path. But when A is updated, it reaches through optimal path. Okay. That's the difference. But still no loops in both the cases. So it looked good. Okay. But we find that that's not always the case. Okay. Right? You can have, when you do FIFR, and we have to come up with a very complicated topology to show, then it causes loops. Okay. So here is it's hard to kind of grasp so many nodes and edges, but let's consider the scenario. Imagine H is the destination. Okay. And if the H is the destination, we'll see that these are the usual next hops. Okay. for the path from A to H would be A, C, C will send it to E, E to F, right? So the packet will go like this. Okay, right? And in the case of here, it will go like this. Okay, from here it will go like that. Okay, right? So for G, it will go like this. Okay, right? Imagine that topology. Now we are showing that FIFR doesn't work in this case. That it has loops in this case. Okay. So these are the back hops. Okay, right? That means if the packet comes from, let's say, F to E, right? That means the link must be down, right? So the next hop is C, right? It'll go like this. Okay, because this is 6. Okay, while this is 3. Okay, follow? So these are all backups. What happens when F sends to E, then E sends to like that. Okay. So now this is the usual, everything is working fine right now. Okay. But now imagine what happens when the link is down. FH is down. Now you tell everybody that link is down, right? So it'll go from 1 to infinity, this one. And now these guys start recomputing. Okay. So our goal is that doesn't matter who recomputes when, whether we have some are in BC, some are in AC state, it should work. But so happens that in this case it doesn't work. Let's see why. Okay. So imagine packet goes from A to H. Okay, right? So it'll go from A to C. Okay, right? It'll go from C to E. Right? So now this guy has already recomputed. Okay, you follow? Right? So according to the recomputation, because this guy is not supposed to send this way. Okay, this guy is supposed to send it this way. You follow that? Because this is down, this guy knows this is down. According to this guy, the shortest path from here should be like that. Okay. So that means if this guy sent it, this guy thinks there's another failure. Okay. This guy already is aware of FH failure. Okay. Follow? Right? And he computed new routes. Now it is preparing for another failure. And try to say, oh, what else must have failed other than that caused this. Okay. So then he'll send it to this. Okay. E will send it to G. Okay. And G is not updated, it's old one. Okay. Right. So this is not unusual. Right. So then it'll send it to D. Right? So this guy will send it in cause a loop. Okay. So this is a scenario where FIFR works normally fine, but it's trying to do convergence during convergence because the guy who computed new paths thinks there's a new failure, not the existing failure. Okay. So that is the problem. Okay. So looping is possible because when you have this AC backups, okay, that means I'm the router in the AC era. I'm the new guy. Okay, I'm in the updated mode. Then I think this is unusual. Okay, right? Based on the new state. Okay, and so usual path treated as unusual unnecessarily. This guy is sending according to the old one. Okay, which should be considered okay. Right? But I treat this as an additional failure and I take some action that causes loops. Okay. So what is our suggestion? You defer the updating of backups. Okay. You update the next hops immediately, but you update the backups later. Okay. So that is what we mean by defer update. Okay. So
are you talking about determining a backup by doing a marker in the header? Like,
oh, no markers.
Okay.
Yeah, very good.
How does the back node know that it's coming from an upstream source?
Doesn't know. It is only that is why you have a loop. Okay. So how does it work to begin with? Is that like okay? What you're asking is how does it work in the first place? Okay.
Well, like if F sends back to J here, how does J know that it's a packet he's already forwarding?
It doesn't know whether this packet or a different packet. All that it knows is you are my next hop. Okay, you are sending me means something failed. There's nothing in the packet.
Okay.
The only context I have is reverse shortest interface along the reverse shortest path. Okay, imagine he is F. Okay, packet is I'm supposed to send me to F should go this way. Packet is somehow coming along the reverse shortest path. From that I can do inference. Okay. So that is my hint. Even though there's no marker in the packet.
Why wouldn't he re-forward it back to F?
Because it came in on the reverse status path, it will take the alternate path. Yeah, so so why you're asking when J gets it, why would it not back send it to F, right? So that is the same thing. Like, let's go back to the original example. No, that is the beauty. The whole benefit comes from exactly. There's nothing in the header, and we still guarantee single link failure or single router failure. That is the whole beauty lies in not having anything in the path. Let's do this. Let's look at this example. Right. Forget convergence. Let's go to the original one. Yeah. So no. Yeah. This is the main thing. No changes anywhere except interface specific forwarding. Okay. So now let's see how this works. Okay. Let's see. Right. So if you look at it, right, doesn't matter where let's say B sends B is. Yeah, again, that is the part of no marking, no tunneling, none of that. Okay. That is the only benefit, by the way. There's nothing else to this. What exactly? That is the one benefit.
Well, the TTL will be incremented, and you already forwarded that sequence number, so that should be enough.
Yeah, but you don't. You're still routing based on the destination and interface. No other context. Yeah, it is possible that TTL is incremented, so decremented, so you have more hops, which would happen anyway. Okay, when you do detour. Okay. So now imagine this, right? Okay, right? So this is down, right? So now packet is going from X to F. Okay, so it go from X to B, right? And then B is rerouting because it knows always the failure, right? Now when B sends to X, what does X send to? X sends to A because the backup is A. Okay.
But to send to A, it has to know that the backup has been invoked. How does it know that?
So every interface has a different forwarding table, right?
But it's on the same interface that it exited.
No. B to A, incoming interface, right? So you can think of, imagine B to A has a line card, right? So the forwarding entry to B to A is different from the forwarding entry from C to A and forwarding entry from D to A.
Sending it and receiving.
Right. Right. Yeah. So you can think of it as like, okay, another way to look at it is A has 4 entries. Okay. One entry, if packet originates at A, where would it send? Okay. Imagine A is the source, where would it send? Yeah. Sorry. How much time we have? Oh, we're past time. Okay. Yeah. We'll wrap it up. Okay. So anyway, good to have this kind of conversation. Yeah. Okay. So now I'll just wrap it up and give a higher level view. So we'll find that without we don't do anything and do FIFR and with convergence, we have a problem sometimes. Okay. So on the other hand, the problem comes from the new AC guys updating AC backups is a problem. Okay. So to deal with that, we defer the update. Okay. Okay, we defer that update, and so that is the idea. Defer the backup update. Okay, so then we'll find that as long as you do it, it works fine. Okay, I'll quickly go through the example. Okay, so when this guy updated, he updated, right? So backup is actually G. Okay, but it won't use that. Okay, right? It'll use the same old backup. Okay. So then we'll find that when packet comes this way, it goes to H, E will send it to C. Okay. Now C will send it to D send it to G, and it'll go like that. Okay. Okay. So everything works correctly. Okay, as long as you defer the backup. Okay. So now it's still possible to have, even with deferred backups, in some cases it's possible. Some other example, right? If all these guys are in DC state, AC state, then it's possible that then the packet goes from I to G, it'll go I, E, D, F, H, like that. Okay. Right. So this can have loops. Okay. So now how do you deal with that? Let's see how often this happens. So we did there are lots of topologies. They're called rocket fuel. It has 6 topologies. There's internet zoo, lot of topologies. These are random topologies. We wanted to see how often this happens. Okay. So this is the performance deferred backup. So basically the idea is what percent of the links that cause loops. Okay. So this is rocket fuel topologies, zoo topologies, random topologies. There's no FIFR, lots of loops. With FIFR, fewer loops. With FIFR plus, which means deferred backups. Okay. We find that in the case of 3 links, this can happen. The strange scenario of these guys are updated, and we try in all possible scenarios. Okay. And then one way to fix that is progressive increments. Okay. So what we are saying is use FIFR, that itself reduces loops. You then use FIFR plus deferred backups, it reduces loops drastically. And then for those simple, small, like a rare scenarios, use progressive link increments. Okay. Here is how it works. Okay. Imagine this is the one that caused the problem, right? It is when you go from 1 to infinity, it causes a problem. So instead of going 1 to infinity, we will go from 1 to 11. Don't ask me why it's 11. It's complicated, right? So then we go from 11 to, okay, no loops, we'll see, right? You go from 1 to 11, okay? And now let's say you go from 11 to 15, okay? Again, there won't be any loops, okay? And then you go from 15 to 17, 15 to 20, okay? Again, there won't be any loops. Then you go from 22 to infinity. Okay. Now it will take this path. Okay. Everything works correctly. Okay. So this is, so now here is a scenario for that link. We needed 4 progressive increments. Okay. So we want to see how many times it causes how many of these cause loops. With FIFR plus plus, no loops. Okay. No link state causes loops with FIFR plus plus because of progressive increments. Okay. And now how often these are, how many times you need, how many increments you need. Okay. So here is the without FIFR, like this is like you need 1 progressive increment. This needs 2 progressive increments like this. With FIFR plus plus, okay, most of the you can see that you don't need progressive increments at all for rocket fuel. No progressive increments needed for internet zoo. Okay, only, yeah, so only except 2 links, we don't, sorry, except two links, we don't need progressive increments. Okay, and in the case of random topology, one link. Okay. And these all with link down. Okay, so now at some point link comes up, that can also cause problems. Okay, so let's go rush it. Okay, so if the link, like this was infinity, the link is down, now link is up, you have to tell everybody link is up. That can cause loops too, even during convergence. Okay, so let's skip this. Okay, so overall there is a way to do this. This is the final summary. Let me show the final transition. Yeah, okay, this is the final transition. Okay, right? So I'm a router, I have LSA, okay, link state advertisement. Is the cost going up, means bad news, or goes from cost is going to infinity, like things like that, is bad news, right? So that is the case of converging down. Okay, right? So metric is increasing. Okay, in that case, install the AC next hops and then install the AC backups after some time. Okay, then it goes to convergence state. On the other hand, if it is a metric decrease LSA, that's a good news. Okay, right? it's like link coming up or link weight decreasing. Then I set the immediate backups to next hops. Okay. And then once I install the AC next hops, I set the backups to the BC backups. And after convergence, okay, after some timeout, I install the backups. So that now I'm ready for another failure. So this is the kind of state transition that each router goes through. Okay. So that's it. Okay. So this is the summary. Okay. Anyway, that was dense.
Thank you.
I hope you got some idea. Any questions?
Oh,
Yeah.
I have one.
Yeah.
So I think the whole point of this is to, what I'm saying, like the class journal, was to show us about AI. Is this, and like you said, you graduated during a time when AI, large language models weren't even a thing when you thought about AI. Would you consider this more of just an advanced algorithm or an intelligent?
Oh yeah. So okay. Yeah.
Intelligent.
What is the difference between AI when I was doing bachelor's and AI now? Is that the question?
Well, that, and how does this relate to that? Would you consider this more of a today's AI or more of
There's no AI
really
here.
advanced?
There's no AI here at all.
Okay.
Yeah. So I'm just saying that instead of talking about AI, I chose to talk about this just to add a different flavor to all the talks. Yeah.
Oh, that's great.
Yeah.
I just wanted to know.
Right.
This is great.
Yeah.
This is
So
really-
now, so coming back to what is the difference between AI in my bachelor's time and the AI now? In the bachelor's time, we thought we know how the brain works. Okay. Right. Imagine, suppose I want to identify a cat. Right. I describe how to identify a cat. Oh, cat should have whiskers, like that. So trying to come up with the rules like that. It so happened that even we don't know how our brain works. Okay. And found out that when you really try to identify cats, it is not the rules that we give from the data, like you give them like millions of cat pictures.
Yeah.
It is able to extract some patterns and identify cats better than humans describing, oh, this is how to identify a cat. In a way, we don't even know how our brain works in identifying a cat, for example.
It's all about patterns.
So huge difference between how when the AI in the past was that we know how to do things. I'll come up with the rules. I'll train the computer to behave like how I think my brain works. Now it's all data, like millions and millions of samples. From that, we're extracting these features and identifying. Now we are trying to understand, how is that working? As if we are trying to understand our own brain through the way how the main brain is working. You understand the difference?
You have to buy a lot of hardware,
Right.
pattern recognition,
Right,
and
exactly.
have to
So right. So when we were doing those things, we didn't have this much power, computational power.
Did you file this as an RFC?
No, yeah. So yeah, that's a good. No, I know. See, again, that's what I'm saying. We are not incentivized for that. Let's say I spend time on RFC. I don't get any like credit for it in my academic progress kind of. Okay. So I can. So one of the ones who praised our work, they said no industry implemented this in the paper like that. So it so happens that there's a IP fast readout RFC. Our idea was done before that RFC was written.
This doesn't, technically, because of how you described it and what you wrote, this doesn't necessarily only have to work for modern internet routing. This is just graph topology in general.
Right, that's true. Yeah.
Oh, so you could apply this to all sorts of.
Yeah, but routing is where we have this. Internet is where we need that. Like you don't high availability, and how do you make sure you have an
drop, come back.
Yeah, like that.
I get it. Okay.
Okay, thank you.
Thanks, sir. Appreciate it.
Appreciate it.